things like that don't go. In addition, make sure you have your goggles on whenever a piece of glass or chemicals are being used. As far as quiz 2 on Friday, the last 20 minutes of class, let's look at that vote list. It just popped up pretty recently on Canvas. So if you hopefully haven't seen it yet, I opened it up when I came down before, maximize. So there are 3 items, meaning there are basically 3 questions, but sometimes they're multi-part. As far as the first, you'll have to be familiar or review macroscopic and particle representations for different states of matter, meaning you could either be looking at them or have to draw them. This includes, of course, includes classification of matter, so that's bundled into that. Then you'll have to be able to produce a particle representation for either a physical or chemical change, it's one or the other. And then the third is metric system conversions, and the extent of it kind of depends on where we get to today. So that could be just simple metric system conversions, like, I don't know, millimeters to nanometers, like that, or it could be a density conversion, but however you think about it, make sure to review the metric system and the prefixes and what they mean. Are there any questions? Yes? These are individual quizzes. It's only the Friday after an exam. 1, 2, and 3, we have a group quiz. Anybody else? There are some seats available. You shouldn't have to sit against the wall. Are we good? That's the campus announcements. It's student view, so you can see it. So make sure to review that material. Leave that, get out of there. Put this guy back up. And we'll continue. Don't forget exam 1 is on Thursday the 25th, 5:30 p.m., 60 minutes in lab 162. The assigned problems, I cut off what we did last time, and this still goes to the end of chapter 1, although I am planning to start chapter 2. There aren't many lecture activity problems near the beginning. In addition, I didn't assign any Moodle Exam 1 homework problems beyond what we already assigned because near the beginning of chapter 2, there aren't a lot of Moodle problems related to that. And I don't plan on getting as far as we need to do to get some little problems in. So that's why it says none for the new, old is 1 through 20. Anything else you may have thought of before we continue? Okay. So last time we were looking at page 23. This time we are starting up on page 24, which, looking at the wrong side again, has to do with density. We have our slide up. Density, of course, is the ratio of mass to volume. Better fix my paper, don't want to confuse people. It is the measurement of the amount of space that a particular amount of matter takes up. So let's think about this more on the particle level. As far as first, mathematically, part A, density equals m over v, or mass over volume. For part B, it asks us what is, or explain what density in terms of the quantity of the matter, and then the space it occupies. So density, the mass proportion, of course, is coming from the amount of matter that's present. All the matter has mass. So the mass is the mass of the particles that are present. In terms of the volume, that's the volume occupied, not necessarily the volume of only the particles. Because for the same pure substance, of course, we get different densities. The density of water vapor is much less than the density of liquid water. We know the density of solid water, ice, is less than liquid water. That has to do with the arrangement of the particles. Therefore, this volume is also including the volume of space between the particles. The reason why gases are so low in density is because the particles are very far apart. We're counting that volume, so it's not just the volume of the particles, which is why density is a macroscopic property, a property of the bulk, needing more than one particle to determine. Remember, a microscopic property, or a property of the particle itself, you only need one particle. You can't use one particle to determine the density of a macroscopic sample. Question?
You said the density does or does not include the space between the particles?
It does. That's why the density of water vapor will be different than the density of liquid water, although it's the same substance. We do have densities of some common substances given to us in table 1.4. We'll find your page and up on the screen. I want you to think about a couple things. First, is density intensive or extensive? Density is intensive. It's independent of amount. 19.3 grams per cubic centimeter. Doesn't matter on how large the sample is, because if you increase the size of the sample, you're going to increase the mass and the volume. They're both going to increase, therefore the ratio of the two stays the same. Part A can be very confusing for students. And I keep meaning to do this, but every semester I forget by the end. There's a particle diagram for gold. Now, in part A, if all the atoms of iron and gold are about the same size and occupy about the same space, what does this mean in terms of the number of atoms in 1 cubic centimeter? We're basically saying on the particle level that iron and gold looks the same. Meaning if I took that image there, I reproduced it next to it and put it in grayscale. So one's iron, one's gold. They would have the same number of atoms. So if our atoms are about the same size and they occupy about the same space, we have the same number of atoms in that constant sample size. Meaning, if we're going to keep our volume constant, phi would equal our mass divided by our density. We can see that the mass and density are directly related to each other. So in part B, which atoms are heavier, the iron and the gold, you can then simply use the density to figure it out. The gold has a higher density, and since the mass and the density are in a ratio, the density is higher, the mass also has to be higher to keep that constant volume. So the gold would be, would have heavier atoms. Using the same logic for osmium, if keep a constant volume, meaning we're assuming the atoms are the same size and take up the same amount of space, we have still a ratio of mass to density. Well, osmium has the highest density noted and also its densest element known. Since it has the highest density, it would be the heaviest atom. Questions? At the bottom of the page is what I put in the lecture activity problem number 19, page 24. They really just want you to reflect on maybe the usefulness of thinking at the particle level to answer the questions that we just talked about. So it's a personal, student-driven answer. We will be using density more often as a conversion factor. This is not in your lecture activity book. If we say the density of gold is 19.3 grams per centimeter cubed, that's for every 1 centimeter cubed, meaning we can use it to convert between mass and volume. It's less likely, maybe a couple Moodle problems, but less likely in practice that you would actually be calculating densities. Our next topic at the top of the next page, briefly, we're going to talk about temperature. We have 3 temperature scales that are shown to us. We have Kelvin, Celsius, and Fahrenheit, simply reading from left to right. In order to understand how to convert between the scales, it's good to think about what's different between the scales. So we're going to compare our temperature scale, and first I want to look at Fahrenheit versus Celsius. When we look at the scales, what's different? Well, the freezing point of water is different, right? On Celsius it's 0, on Fahrenheit it's 32. It's easier to kind of remember that difference, but we also have differences in all of these noted temperatures. I like to call the 0 Celsius the 0 point in a way, and therefore it's not the same on Fahrenheit. We have a difference in what I like to call the 0 point. Meaning 0 degrees Celsius equaling 32 degrees Fahrenheit. Meaning when you convert, you're of course going to have to compensate for that difference. We also have a difference in the, what I would say, step size, or you can think about it as the degree size, think of whole numbers. When you take 100 Celsius, 0 Celsius, that's 100 degrees. If you take 212 Fahrenheit, 32 Fahrenheit, that's more than 100 degrees, or 100 steps. So we have a difference in the step size, or degree size if you prefer. Meaning, in order to convert, you're going to have to compensate for that. Just as a note, we have between boiling water and freezing water on the Celsius scale, we have things that we have to compensate for. Degrees Fahrenheit equals degrees Celsius times, I wrote it backwards, so let me fix it. The way you usually see it is degrees Fahrenheit equals 9/5 degrees Celsius plus 32. The 32 is compensating for that 0-point difference. With 0 Celsius, you have to use 32 to get Fahrenheit. The 9/5 is 180 divided by 100, reduced. I also see the Fahrenheit scale as a bit of a, it's not English per se, but remember I said that all English to English and English to metric conversions are given to you? I see it English-ish. And I see Celsius as metric-ish, meaning it'll be given to you. We don't usually report our data in Fahrenheit. So this is a given equation if needed. Meaning, I usually don't use it. But if you would need it for a quiz or exam, it would be given to you. Who's questions? Let's compare Celsius versus Kelvin. I'm trying to get that line to the top so I don't lose that information. So, degrees Celsius versus Kelvin. What differences do we have? The heat. Well, we know difference in 0 point, right? 0 Celsius is not 0 Kelvin. Does anyone know what 0 Kelvin is called? Absolute zero. Do we have negative values of Kelvin? No. That's actually a really good thing to remember and help you determine if you converted incorrectly. Well, so we do have a difference in what I call that 0 point, right? Our 0 degrees Celsius equals 273. I couldn't remember if this slide had the 0.15 on it, so I'll fix that, got a little messy. 0 degrees Celsius equals 273 Kelvin. I know you may have been taught the 273.15 in the past. Usually it doesn't affect sig figs at all, so if you want to just use 273, it's perfectly fine. If you want to use 273.15, it's perfectly fine. Is there a difference in the step size? Or the number of steps? I can't really say degrees here because we use the word degree with Kelvin. 373 down to 273 is 100 units, right? 100 Celsius down to 0 Celsius is 100 units. So there's no difference in the step size. Meaning we only have one difference to compensate for, and that is a much easier equation. Kelvin equals 3 Celsius plus 273. That is neat to know. Because we use it much more often. And you will need to know it in future classes as well, so I'm not even making you learn it now. In case you don't already know. Yes?
273 is good enough, we don't need to know 273.
Yeah, as I just said, if you want to use 273, that's perfectly fine. If you want to use 273.15, that's also perfectly fine. It's usually without change sig figs. Anybody else? So, just to be clear, that will not be given to you, okay? I put 21 and 22 up on the list of electroactivity problems. Remember how those work? If you think you need to practice, then practice. If you don't think you need to practice, then don't practice. But the table number 21 is completed in those electroactivity released answers. So if you want to play around with putting the equations together and whatnot and see if you get it right, that's perfectly fine. The answers, of course, of 22 are there also. Then we're going to move to that page 26. Make sure you're comfortable with the rules associated with converting between scientific and standard decimal notation, as well as the rules for exponents when using mathematical operations. We reviewed the exponents a little bit. As I said, I usually would not require something to be in scientific notation. There's some numbers that are just so big and some others that are so small that you specifically for SIGFIGs on quizzes or exams. Sometimes it will tell you to report your answers to so many SIGFIGs, and that is just to try to avoid students putting everything their calculator shows us into the answer box. It's to ease grading, meaning if you didn't do it right, we're not going to actually mark off. Where SIGFIGs are important is lab, because the whole reason for significant figures and significant digits is to preserve the precision of the number that came from a measuring device. So therefore you do have some practice. One is very simple in part A, but notice the lab application actually goes on to the next page. It's really important for a lab to preserve the precision of the measuring devices you're using. Just so you know, in my exams, you'll basically be told, students are expected to round reasonably, meaning if it's not an exact number, don't round it to a whole number, leave a decimal place or two. Okay, but don't give us everything in your calculator either. It just makes grading quicker and easier. So if you think you need to practice a little bit, then practice a little bit. Any questions? Making sure I'm not missing a hand. Not used to the big group after a small summer. Remember on this page. Remember equivalencies and the rules governing these. Make sure to test yourself while you have anchored understanding actual problem using your unit conversions so you can be more confident when you're working in the abstract, meaning when it's easier things that we kind of understand the problem and we're not brand new things in a couple weeks. Practice your dimensional analysis and unit analysis now. Because when things become abstract or brand new to you, you've got good habits of always writing your units and casting things out now. It will help you when things are brand new. We do also have a problem-solving strategy for you. Everybody will develop their own, or already might have their own, and I even change this sometimes depending on the problem. Of course, when you're looking at the problem, make sure to identify the problem. Read the problem. Most problems in Chem 102 are not just like a sentence or two. Sometimes they're paragraphs. Sometimes you have to search and say, what is this asking me for? When you're reading, make sure to determine what you need to do. It can be confusing. Identify what you're given and what's needed. Sometimes you're given information in the problem itself that you'll need to use. Sometimes you're given the information in the product itself that you don't need to use. Also, by what you need, do I need to pull some metric conversions out of my head? If it's Moodle, do I need to pull some English to English or English to metric conversions out of my book? Determine how to set up the solution. Determine how to set the solution. Sometimes pictures are used, sometimes just flows. I'm going to go from this to this to this. I'm going to use this conversion to do that step. If you actually think about the process before you do the process, you're more likely to get the right answer. And then calculate or determine your answer. Notice that is not the last step. Report your answer. Remember units. Whether it's a quiz, discussion, half sheet, exam, or lab, if there's no units, it's not right. The number means nothing without the units. If it's lab, also check your SIGFIGs to make sure you're preserving the precision of the measuring devices used. And the last step is check your answer. Did you actually answer the question? Go back and say, okay, this is what they asked for, is that where I got to? So often students stop a little early and they're not quite to the answer yet. But also make sure your answer makes sense. Is it reasonable? And since I have 2 lectures, I can't remember which example I used in which lecture, but if I was trying to calculate the mass of an atom and I got some positive exponent worth of grams, that's not reasonable. That's a really huge atom. That might have been a negative. I might have flipped the conversion factor somewhere. Let me go back and double check. Make sure you check your answer and say, does this make sense? We are going to do some practice problems, don't worry. Any questions? Of course, we'll develop your own. But just like science, make it stepwise so you don't forget to do something. The next page and the page after that, we're putting up this lecture activity problems. Number 25 on page 29 is just having you convert everything to meters and then ordering by size. So it's nice practice for conversions, especially for that quiz coming up. And then number 26 through 32 is more scale idea type things. And if you want to think about that after you do your scale activity in lab next week, that is perfectly fine. and viruses because they're inside the viruses. So you might have to keep them on. They're on water molecules next to this thing. So just think about them, at least read through them, make sure they kind of make sense. Good? We're going to be doing number 33 practice problem. I'm going to actually put the problem on the center screen so not everybody on that side of the room has to crane their necks. I should leave it over there as well because you have all the information given to you. So let me go dot camera, built in. If there's something that is on this slide, I think everything's actually typed out for you, then I'll let you know. Okay, there we go. So we're going to be painting, we are painting a very strange room. We basically put a box on top of the painter because no windows and no door. We're not painting the floor. We're painting the four walls and the ceiling, and we're using a gallon of paint. The question is asking us what is the thickness in micrometers of the wet paint. Now, this is your first kind of introduction to lecture activity problems per se. Often we'll have a whole page that kind of steps us through the problems. I will, of course, follow the logic of the page. But if you think of a different way of doing the problem, it's perfectly fine. There's always more than one way to do a problem. There's actually a different way for this one. My brain likes better, but I will follow this path. So we're being stepped through this. We're asked to, first off, determine what the area to be painted is. And we're going to ask to calculate this in square feet. We're painting four walls and a ceiling, and all the dimensions are the same, 12 by 12. So for part A, we would have 12 feet by 12 feet, but we have 5 surfaces. If each is 12 by 12, then we have to paint the walls and the ceiling. So 12 times 12 times 5 would be 750 square feet. Hopefully we're good on that one. We're going to move that down just a little bit. It seems really high. Question? Did I just write something wrong? Yes, I did. My brain put a different number in place. Thank you very much. Don't be afraid. My brain likes to do that a lot, so I don't mind. 720. In the next step, we're asked to convert this to meters squared. This is good practice for things that might show up on Friday. So we are going to take, in part B, our 720 square feet, and we're going to use conversion factors to get where we want. Now notice up by the typed area, since you don't have the screen in the middle right now, we have given to us 1 inch equals 2.554 centimeters, 1 quart equals 0.9463 liters, and 4 quarts equals a gallon. Another one that was actually typed on the screen was 12 inches equals 1 foot. So there was a piece of missing information there. And we're going to be using that for our first step. If you're unsure what to do, look at the unit you have, look at what you're given and say, where is that unit? On the screen, we have 12 inches equals 1 foot. So 12 inches over 1 foot. But this is square feet area. This is one-dimensional length. So we will have to square that to get area. Now we have inches. Look at what I got. Oh, I got something with inches. I got 2.54 centimeters equals an inch. 2.54 centimeters over 1 inch. But again, we have area here. This is one-dimensional length, so we'll have to square that to get area. That gives us the centimeters squared, but I want meters squared. Now you're pulling something out of your head. I have to remember there are 100 centimeters in a meter. That would not be given information. So 1 meter, or 10 squared centimeters. But again, these are length units, so we need to have area, so we need to square it. So into your calculator, you put in 720 times 12 times 12 times 2.54 times 2.54, divide by 100 twice, we'll have the answer of 66.89 meters squared. I strongly suggest that you don't introduce rounding errors, you do it all at once. So 720 times 12, square it, so times 12 twice, times 2.54, times 2.54. This is the denominator, so divide by 100 2 times. What was that?
Minus 10 centimeters squared.
This unit?
Yeah.
This is length, but we have area. We have square feet, and squared inches, squared centimeters, so we need square meters.
Right.
It's very...
Like the exponent
person, so I just had to write things in exponents, so I don't mind, just ask, okay? It also makes math a little easier once you kind of remember your rules for exponents. Like if you've got your calculator for something, everything's in metric, it's just, hey, I can just use my powers and do the math. Any other questions? Next, they're asking us for the volume. I like to take a little pause here. Well, first I'll actually answer. And the question itself, we're told we're using 1 gallon. The reason why we're going volume now is because we're trying to find thickness. And if we remember, volume equals length times width times height. And if you want to think of the height as the thickness of the paint away from the wall, this would be our thickness. And that is our area. So we've already found the area, now we need to find the volume, because that will then be only one unknown and help us find our thickness, which of course we can rearrange for. Thickness equals, we're going to be divided by the area, volume divided by area. And when we divide, we need to have like units. So if you look in part D, they're asking us to convert the volume to meters cubed. We have meters squared, we have meters cubed. X cubed over x squared would give us x. X will be our thickness, or meters. So let's convert our gallons. Making sure I'm still up there? Okay. I'm checking your given information. You were given 4 quarts equals a gallon. We also have that quart to liter conversion. Once we're at liters, then we can know use what should be in our head. So we know that 1 gallon from the given information equals 4 quarts. So now we can continue from our quarts. We're given 0.9463 liters for 1 quart. We also then know how to get to milliliters from liters. The reason why I want to do that is because 1 centimeter cubed equals 1 milliliter. Need to know. So I'm going to go to milliliters first. We have 1,000 milliliters in 1 liter. From this right here, we know that every 1 centimeter cubed is equivalent to a milliliter. And now I can use my one-dimensional conversion of 100 centimeters to a meter, and then just simply cube that. Or 10 squared centimeters from here. So 1 meter over 100 centimeter. That's length. We need volume. So we're going to cube the last one. And actually, I can put the answer at the bottom. Meaning, if we put into our calculator 4 times 0.9463 times 1,000, and to divide by 100 3 times, we will get our answer for the volume in terms of meters cubed. And hopefully you get 0.00379. We have the area in a meter unit. We can now divide the thickness in meters. Any questions before we do that? I'm going to have to move the sheet up a little bit. Actually, I can unzoom a little bit. I don't want to make it too much smaller though. I'd rather move the sheet up and keep it big. Any hands? Bless you. So this would then be part E. We already determined that thickness is volume over area. So put our volume in, 0.00379 meters cubed, divide by the area that we found that I almost bumped off the screen, 66.89 meters squared. And this will give our thickness in meters, 35.666 times 10 to the negative fifth. Or 5.66 if you prefer. Yes?
Sorry, is that 66.89 or
66.89.
29?
It was a little messy at the top, wasn't it? A little bit better than 8? Okay. The last step is to get into the micrometers. So for part F, am I still on the screen? Almost there, I have to move up just a little bit. We have 5.666 times 10 to the negative fifth meters. now have to pull out our head that we have to remember that micro is 1,000,000. So we have 10 to the 6th micrometers for 1 meter. And this will then move our decimal point 6 places or eliminate this -5 and move our decimal point 1 place. Meaning 5.67, oops, no, I forgot to move my decimal point, 56.7 micrometers, or with sig figs for the question, 57 micrometers. The only reason I did it set it like that is because we have our dimensions of just 12 feet by 12 feet, 2 sig figs at the beginning. But again, quiz or exam will be very specifically for 6 students, so 56.7 will be perfectly fine. It's a nice question to demonstrate, all has nothing to do with chemistry, to demonstrate how lengthy the questions could be. And by the way, you would only be given those first couple lines and the metric, or sorry, English to English or English to metric conversions that were needed. Any questions? So I have another one. Not quite as hard, or not quite as detailed. There is one similar to this in Moodle, I believe, and there's one similar to the discussion worksheet, so you get a little more practice with it. The next one we want to do is on page 32. Number 34. Make sure you're giving all the information on your sheet. There'll be a couple of the conversions we use here that we're using. They were on the screen, but again, so nobody's at a deficit. I want to keep the writing up on the screen. So I'll remind you when there's something on the slide that it would be given. So 34 asks us, and as you said, Moodle homework problem number 6. What is the mass in kilograms of helium if it filled a square room, if the room has walls that are 9.57 feet high and 9.57 feet long, and the density of helium is 0.18 grams per liter? And again, we're going to do this in parts. You could think of a different way to do the problem, but we're going to follow the sheet so we don't confuse as many students. So the first thing they're asking us to do in part A is what is the volume of the room in cubic feet? Well, we're given the dimensions, and we can know that they're the same, so this is actually a cube room, not just a square room. So to get that volume, 9.57 feet cubed. And that would give us 876 cubic feet. So now we're just going to get this to liters in part B. We're going to, of course, have some English to English conversions that were given to us. Again, I will show exactly which ones were given on the slide. So for part B, we're starting where we left off, 876 cubic feet. Well, we just used one last problem of 12 inches in a foot. That connects to our feet. 12 inches in 1 foot, and that was given on the slide. Of course, this is length, that's length, this is volume, so we need to cube. Another one that was given on the slide is 2.54 centimeters in an inch. That connects to our inches, so that's our next step. 2.54 centimeters in 1 inch, and again, that was given on the slide, but this is length. We need volume, so we must cube. Now we would have to be at centimeters cubed. Now we're going to the point of digging out of our brains. Well, we know that there's 1 milliliter for every 1 centimeter cubed. That gets us to milliliters, and we're asked for liters, so we have one more step. 1 liter has or contains 8,000 milliliters. So if we take our 876 and we multiply by 12 3 times, and we multiply by 2.54 3 times, and divide by 1,000, we get our answer in liters. 2.48 times 10 to the 4th liters. Yes?
So those last two do not need to be cubed?
No, because they're already volume. Milliliters and liters are already volume units. When we had length, we had to cube it to get to volume. Yes?
So when we're always finding volume, we're always like cube it.
If it's a length unit, yes. I only say it that way so that you don't cube the volume units. Okay? Anybody else? probably want to put that together to one step, which is fine. So for D, we're just using this conversion factor. We have our 2.48 times 10 to the 4th liters. Well, we know we have 0.18 grams for every 1 liter. Therefore, that tells us we have 4.47 times 10 to the 3rd grams. Yes, right over there. I'm sorry, I didn't see you. I know I zoomed it out to get the whole problem on the page, and as I was writing, I think part B is like, oh, I forgot to put the thing back down. Is that better?
Yeah.
Okay. I can do a little more. I don't want to be squinting. Let me get it down just a little more. Let me focus it. Doing that sometimes makes it blurry. Better? Okay. Anybody else? So the last step is just asking us to convert this to kilograms. How many grams are in a kilogram? 1,000. We didn't really deal with that too much last time, right? So for part E, we're starting where we left off. Our 4.47 times 10 to the 3rd grams. And we're going to kilograms, so 1 kilogram over 1,000 grams. Meaning we're dividing our answer from before by 1,000, meaning this and this go away. So 4.47 kilograms, or if you want to go with the sig figs, that would be 4.5 kilograms because we had the 0.18 given to us as the density. Just another example of more lengthy problems that we might be used to, like just one sentence. Convert this to that. Are there any questions? And I'm pausing because I see people still writing. Another thing that is sprinkled throughout the lecture activity book is not only, some practice problems, but also, if you look at page 33, I don't think we've come across anything yet, maybe I forgot. Number 37 has 2 multiple choice problems that have been used on past exams, meaning we're trying to expose you, in addition to the discussion questions that you'll be seeing at the beginning of every discussion, to more multiple choice problems. The more of them you see and work through, the quicker things will be, because multiple choice problems are typically written to be done within a minute, if not less. So you do have 37, those 2, plus 35. Oh, I wanted to mention 35. It says chapter summary, question number 2. That's coming from your yellow section of your course manual. Whereas the homework problems are the end of chapter problems, and the, forgot what they're called, the review week problems are within the text. So chapter summaries questions are coming from within the yellow section of your course manual, so number 2, page 4. Another thing I want to make note to you. We haven't taken these out of the lecture activity book yet because they might come useful again, but page 34 says spot review question chapter 1. This was from pre-COVID. We used to make students pay for an app to answer questions we could take attendance. We don't, of course, make you pay for that anymore, and I was actually very happy coming back from lockdown and saying, thank God I don't have to make the students pay for that anymore, because every dime you have to pay, because the dime you don't have something for something else. I'd like to have to make you pay for that. But leave them in here in case the instructor ever wants to do that again. You can ignore them, or you can try to work them, and then just send me an email and say, hey, did I get this right for a picture? That'd be perfectly fine. But I don't have the answers up on Canvas, because don't think many students are doing that. So you can just ignore the spot review problem pages, which will be throughout the whole thing. We good? That's the end of chapter 1. We still have about 6 minutes or so. We can start the intro chapter 2. We won't get a lot done, which is why I didn't put lecture activity problems in chapter 2 in. Good? So you have a good idea of what we're talking about next time, and we will get to a big chunk next time before the quiz. So again, we're going to start chapter 1. Let's look at the chapter. Oh, dang it, it's not up there anymore. Let me put it up. Oh, I can't wait to fix it on the projector. It's not right hand, the key will get this side. There we go. Oh, this is a chapter that we really do need to look at the slides. There are some changes. So we have 6 sections that we go through in class. but you won't be tested on it, and realize that the nomenclature will be done between video, a discussion, and a little bit in class. Any questions about that? So if we go to page 36, number 1 says, matter is not continuous. What does this mean? This means that if I had, let's say, a pure substance, let's say a bar of pure iron, and I kept cutting the bar of iron in half, cut it in half once, shorter length, cut it in half again, and kept doing that. And I was able to somehow get the right instruments to keep cutting it in half. I would get to a point where if I cut it in half, it no longer would be iron. I get the atom, right? And you cut that in half, you have different substances. Meaning, matter is not continuous when you get down to a fundamental particle that we now know to be the atom. Is it supported by what we can observe macroscopically? No. I'd eventually have to get some kind of instruments to keep cutting, to get to a piece that's so small that we can no longer see it. Meaning, nothing that we know about atoms has been seen. It's all macroscopic observations of data that is hopefully interpreting what is going on in the particle level. I say hopefully because the way I teach things now is different than the way I was taught, because things have been learned constantly. As far as number 2, the definition of the atom, smallest piece of matter that retains the properties of that type of matter. You could, of course, use your own personalized definition. Just make sure they're actually giving you the right idea. Saw as being an atom has changed drastically over time. So we're trying to make it nice and generic right now. We're going to introduce the first scientific theory as to what was on the particle level, what atoms were. We'll read through basically number 3, and then we'll be done. So if this is what you have in number 3, Dalton was the first person to put together a scientifically supported theory, or atomic theory by scientifically supported, meaning there's natural laws embedded, which we'll explore more next time. He had 4 hypotheses. Some textbooks call them statements, some textbooks call them postulates. Our textbook calls it hypotheses. Elements are comprised of atoms, and atoms are the smallest pieces of matter. Well, we know that's not true anymore, right? There's pieces of matter that are smaller than that, but at the time, that's what they thought. So he was hypothesizing there. So as far as the particulate diagram, when you're doing something for atoms, it should be more than one, because we know there's different variations of atoms, right? So it's a collection of atoms that gives us an element. Atoms of the same type, number 2, meaning the same element, have the same properties, size, mass, and chemical properties. Why atoms of a different type, a different element, have different properties? Well, now we know that not all the atoms of the same element have the same properties. We'll investigate that more next time, but in terms of particle diagrams, to show that we're comparing 2 elements, 2 different color symbols. Not necessarily mixed together, just 2 different color symbols. In number 3, compounds are formed with whole combinations of atoms of more than one element. In any compound, the ratio or expression is always integers or simple fractions. So here, for the particle diagram, I decided to show 2 different compounds being formed from our 2 different colored atoms above. But we know it's always going to be in whole numbers because atoms are whole entities. And actually, number 3 is coming from 2 natural laws that we'll look at next time. And as far as number 4, atoms cannot be created or destroyed in chemical reactions. Therefore, chemical reactions involve the rearrangement of atoms do not create the destruction of them. So I'm showing a chemical change or a chemical reaction for one of our compounds.